Let's get back to work. This is number 26 from chapter 20. We're still working through the exercises here. Exercises are supposed to be a little bit less challenging than the problems. Today is, let's see, this is Friday. Your exam's on Monday, coming up soon. Okay, we're told in this problem that we're dealing with 10 grams of neon and that the total energy of this quantity of neon is 1,700 joules. Well, hopefully you know from perhaps a class of chemistry or a couple tables in the chapter that neon is a monatomic gas. So each of those atoms, think of it as a little sphere. It can move left and right, up and down, into the page, out of the page, and that's it. There's no energy associated with rotation or vibration. So it's got 3 degrees of freedom. We may or may not need that. For an ideal gas, remember, we pretend that these gas particles, they're quite far apart from each other usually. They don't interact, so none of the energy of this gas is tied up in potential energy. It's all kinetic. But we also know that kinetic energy is measured by the temperature of a gas. So if we know the temperature, perhaps we can find the energy. Since the energy is purely kinetic, if we could calculate the average kinetic energy of these various gas particles, so this is per, let's say, kinetic energy per particle. And I'm using the same notation that your solutions manual uses. I'm not sure why they go with the capital K, because don't they often use that epsilon instead? I'll do both. If we could figure out the average kinetic energy per particle and then just multiply by how many particles there were, we would have it. That would be the total thermal energy, because again, there is no potential energy for an ideal gas. It's all kinetic. The kinetic energy alone is what determines the total energy. So the alternate notation would be the number of particles times the average energy per particle. Your book likes to use that. Now, if you don't quite see this, just flip this around. Isn't this the definition of the average energy? You would take the total energy and divide it by the number of particles. That's how you find an average anyway. Of course, in this case, we're talking about a really big number. Okay, so all that remains is to find that average energy. Well, we've got a couple formulas. We know that for a monatomic gas, the average kinetic energy, that's epsilon in parentheses, should be 3/2 kT, because there are 3 degrees of freedom, but it should also be 1/2 mv squared average. Each particle has a different speed. Remember, there are many, many particles and they all have slightly different speeds, but we could look at the average value of all those kinetic energies. And I've gone through this before, but you can take the 1/2 m out, and when you average the square of the speed, that's the same as, by definition, the RMS speed squared. I'm using this fact. VRMS is the square root of the average value of the squared speed. So calculate the average value of V squared. Take the square root of that. That's V root mean squared. If you square both sides, then you get this correspondence. Okay, now the problem is asking, I'm sorry, they didn't actually ask for VRMS. They asked for V average. What is the average speed? Well, the average speed is a little different than the square root of the average squared speed. They're similar. Look to your book for a fuller discussion. They don't actually go through all the calculations. It takes some fancy integrals to calculate these average values. You could find those in like a junior level book on statistical mechanics or thermodynamics. So the problem, if you read the language carefully, they're saying estimate the average speed. So we're just going to use the fact that the average speed is roughly equal to the RMS speed. There's something like 10% different from each other. No big deal. Okay, so the average, or excuse me, the total thermal energy would be the number of particles times the average value of the kinetic energy of the particles. And that's just going to be N times 1/2 m VRMS squared. In other words, VRMS would be the square root of 2 times the total energy over M. And I left out the N, didn't I? Okay, in order to evaluate this, we need to know what all these numbers are. They gave us the total thermal energy. We know how many joules we're dealing with. They didn't tell us how many particles we're talking about. And sorry, they didn't tell us the total number of neon atoms that we're dealing with, but they did tell us how many grams. So this is where we can convert grams into number of particles. That's where Avogadro's number comes in. So I'm going to consult the periodic table. Yeah, how awesome is this thing? Let me get rid of the video panel here. I just Googled online periodic table, and here we go. Hey, it even looks like Breaking Bad. Or wait a minute, is Breaking Bad emulating the periodic table? Which way does it go? Art imitating life, or the other way around? Neon is over here. They tell us it's got atomic number 10 protons, but I can't move my mouse over here, and you can't see my finger pointing, so just look off towards the left side of the screen where the icon for neon is enlarged. Under the name neon, it says 20.18. That's an average value. I'm sure many of you know that's an average value for the atomic mass number. It's an average because there are different isotopes. Most neon atoms, evidently, would have 10 neutrons along with their 10 protons, giving them an atomic mass number of 20. But some isotopes would have, let's say, 11 neutrons. So we'll just go with the most common one, 20. And now we know what the atomic mass of a neon atom is. Now what I could do here is calculate N and plug in M, little m, this is the mass per particle, in kilograms. Okay, sorry about the awkward pause here. Zoom quit on me. So let's resume with Zoom. I could calculate the total number of particles, plug that in, and plug in the mass of each neon atom in kilograms, but maybe I can combine these and circumvent some steps. Let's see how that works. Wouldn't the total number of particles be the same as the number of moles times the number of particles in a mole? This is capital N. Number of moles times how many particles are in a mole would be the total number of particles. And then I can do this. I could take the number of particles in a mole times the mass of each particle, and that would be the mass per mole. So over here I'm using Avogadro's number times the mass of an individual particle would be the mass per mole. So this is really just N times the mass per mole. Great, so now I can plug that in here and not have to mess with the actual mass of a neutron, or excuse me, a nucleon in kilograms. You know, the 1.66 times 10 to the negative 27. We don't actually need to deal with that because I've circumvented it here. Okay, so the average speed is roughly the same as VRMS, which we just determined would be exactly 2 times the total thermal energy over number of moles times the mass per mole. And that's the beauty of this convention, that 12 grams of carbon is exactly 1 mole, because now, since we recognize that neon, what was it, neon 10 protons, 20 nucleons, 1 mole would have a mass of 20 grams. And I'm not sure about the placement of the 20. That depends who you ask. Let's plug in numbers here. 2 times 1700 joules times, and we've got, oh, darn it. I do have to mess with that, don't I? Because we need to figure out how many moles we're talking about. That's not bad. I'll do that off the side here. 10 grams of neon times 1 mole for every 20 grams is half a mole. But then when we multiply by the molar mass, is there even a simpler way to do this, I wonder? Probably, but in any case, down here we've got half a mole times 20 grams per mole. And am I just going around in circles here? I feel like I'm going around in circles. I think I am going around in circles because 1/2 times 20 grams is 10 grams. That's the mass that we started with. So evidently this denominator is just the total mass. Is that what's happening here? But that does make sense from this formula. If we take the mass of an individual neon atom and multiply by how many neon atoms we have, that would just be the total mass that we're dealing with. So I could have just put capital M here. Interesting. Yeah, your solutions manual does not seem to recognize that. I'm looking at their solution, and they don't do it that way. Aha, but I made a note. Yep, I did make that observation. Okay, so we could have just plugged in the total mass. It's nice to be on the lookout for these simplifications if you can. So I'm going to take 3,400 joules up top and divide that by, make sure you're in SI units, right? If you want your speed to come out in meters per second, this has got to be SI units. So 10 grams is 10 thousandths of a kilogram. I'll take the square root, and I get a very reasonable number. So that's the RMS speed, which is not the same as average speed, but they're close enough. So we've estimated the average speed of these particles. This next problem has a fun result, although the result is not really explored in the prompt. They're asking us to calculate the thermal energy associated with all the air particles in a typical room full of air. So they give us the dimensions of the room, 3 meters high. That's a bit of a low ceiling, but it's still more or less the dimensions of a typical, let's say, a bedroom. And because all those particles are at room temperature, they're all moving around with some average kinetic energy, which we can easily calculate. Take that average kinetic energy, multiply it by the total number of particles, and that would give you the total kinetic energy of all the particles in that room. Now, that's randomized energy. It's very different from, like, suppose you could make all these air particles stop in their tracks. They just fall to the floor. First of all, that'd be an awful lot of particles. But if you could then take them, squish them together into a big ball of air particles, and then get them moving to the left, since there's no room to go right on the page, but get them all moving in a single direction together, just like a rock that you've thrown. Then you could very easily calculate their kinetic energy, 1/2 mv squared, where m would be the total mass of all the particles, and v would be whatever speed you chose. Now we could choose as that speed the RMS speed of all these particles. So we could use the temperature to figure out what the average speed basically is for all these air particles, and then imagine what would happen if you stuck them all together into a big single mass and got them moving at that speed and calculate the kinetic energy. And you're going to be surprised at just how high that energy is. There's a considerable amount of energy just hanging out in your room in the form of thermal energy. But the reason that we're all unaware of it is because it's not usable energy. Well, you could use it to drive some sort of heat engine, but you would need, we're going to see in the next chapter, you would need a much colder reservoir, like ice water, in order to draw that energy out. And it wouldn't be very efficient, and you wouldn't be able to use much of the energy. But you will be surprised at how much energy actually is contained in the submicroscopic kinetic energies of all those particles. Okay, so maybe the first thing we should do is figure out how many particles we're talking about. They gave us, indirectly, they gave us the volume. So we've got V. They gave us the temperature, that's T. You should already be thinking about the ideal gas law, PV equals nRT. So I could write the per particle version and capital N KT. We could use either one. I would like to solve instead for the number of moles N. And a subtle point that may not be addressed in your book is that you can use, evidently, you can use this equation even if you're talking about a mixture of ideal gases, which is what air is. Air is not just nitrogen or just oxygen. There's 3 or 4 components, probably more than that because you've got water vapor, carbon dioxide, argon. That's pretty much all I know. Can we plug all these numbers in? We're given the temperature, we know R. Pressure, what are we supposed to do with pressure? They didn't give us that. We just assume it's atmospheric pressure because there's no mention of any special circumstance. Okay, so we've got our 1.01 times 10 to the 5th pascals. And then for the volume, I'll do it this way. Can I do it in my head? 6 times 8 is 48. 48 times 3, that would be 40 times 3 plus 3 times, or 8 times 3, 24 plus 120. I think that's 140. Let's see, 144. 6 times 8 times 3, 144 cubic meters. 8.31 joules per mole per Kelvin times the temperature. Remember, it's got to be absolute temperature if you're going to use the ideal gas law, 293 kelvins. And if you were to examine these units in detail, you'd see that they do actually cancel out the way they're supposed to, and moles would come out up top. The following number for the number of moles: 5,973. That seems a little on the high side. But I checked your solution manual and they get a very similar number. Actually, they get a slightly higher number, and it's because they included the 3 here. Maybe I should have kept that extra sig fig. Fine, I'll go with their value of 5,991 moles. And now what are we supposed to do with that? I will remind you of this all-important result from the chapter, the equipartition theorem. I misspelled that in a previous video. Equipartition. The theorem says, and this comes from statistical mechanics, it's not proven in your chapter, it's just quoted. We're told that the number of, or I could have said the number of joules, but I'll say the amount of energy associated with each particle is 1/2 kT per degree of freedom. Remember, for a monatomic gas, where's my rubber ball here? I'll use the eraser. If this is a single atom of argon, for instance, it can move this way, this way, this way. It's got 3 degrees of freedom, but there would be 1/2 kT joules of energy associated with this particle per degree of freedom. So that would be a total of 3/2 kT per particle. And remember, even 300 kelvins times 10 to the negative 23rd gives us that appropriately small amount of energy per particle. Well, what if you want to know the total energy per degree of freedom per mole? You would just take the energy per degree of freedom per particle and multiply by the number of particles. But the number of particles would be how many moles you've got times Avogadro's number times the 1/2 kT. But then we can take Avogadro's number and multiply by K, and that's the same as the universal gas constant. So this is really 1/2 N RT. Am I doing this right? Yes. So this would be the amount of energy associated with all the particles per degree of freedom. But what if you just want to know the amount of energy per degree of freedom per mole? Then you would divide by the number of moles. So just divide out the N. And this is what I was working towards. So I would memorize both of these. At temperature, absolute temperature T, this is how many joules of energy are associated on average with each degree of freedom for each particle. This is each degree of freedom for each mole. So I'll put joules per mole per degree of freedom. Memorize it. 1/2 kT, 1/2 RT per mole, per particle, per degree of freedom. It's not a very complicated formula. If you can just remember that, so much more of this chapter will make sense to you. Okay, so back to the problem at hand. We know how many moles we've got now. And since we know the absolute temperature, we can easily determine how much energy there is per mole per degree of freedom. But the difference now is that we're talking about air. And air is composed of between 70 and 80% diatomic nitrogen, so 2 nitrogen atoms stuck together, diatomic oxygen. Is there some diatomic hydrogen in there? I think very little, because I think it tends to explode with oxygen. I should know this. So here is my model of a diatomic molecule. A couple of little Christmas ornaments here. And we have to talk about the degrees of freedom. So just like a monatomic gas atom, this thing is free to do this, translate along the X, translate along the Y, translate along the Z. So at the very minimum, it's got 3 degrees of freedom, but at sufficiently high temperatures, it's also able to do this, consider an axis coming out of the page here. It's free to rotate about that axis. So it's got this additional rotational degree of freedom. That's 4 degrees of freedom already, but I could just take this axis, rotate it by 90 degrees. It's also free to do this. Okay, so we've got this rotation and this rotation. The other axis doesn't count. This one does not count as a degree of freedom. And I guess there's a couple ways to think about that. Number one, if these particles really are tiny, then is there even any energy associated with this? Think about the moment of inertia if you think back to mechanics. I think there's a more sophisticated quantum explanation for why this doesn't count, but let's just run with the result. Let's just accept it, which is what we kind of have to do at this level of rigor in physics. So I count a total of 5 degrees of freedom. And it's important to observe that that's true at room temperature. At room temperature, a typical diatomic molecule has 5 degrees of freedom, 3 translational, 2 rotational. If you make the gas hot enough, some additional degrees of freedom will kick in. This molecule will then be free to oscillate. And then it's like a spring and you've got 2 more degrees of freedom. That shows up later in the discussion. Okay, so since we've got 1/2 RT per mole per degree of freedom, the total thermal energy in the room should be 5/2 RT joules per degree of, no, not per degree of freedom because I've already multiplied by the number of degrees of freedom. 5/2 RT joules of energy per mole times the number of moles. Simple as that. So if you just keep the equipartition theorem in mind and remember those formulas, you're good to go. Let's calculate how much energy we're talking about here. We've already determined 5991 moles, 8.31 joules for every mole for every Kelvin, and then 20 degrees Celsius is 293 kelvins, and this will come out in SI units. Okay, count the decimal places here. 3, 6. I get 36.46 megajoules. Yeah, your book gets a similar value. It's 36 million joules. And I chose to write it that way because I will remind you, you take remember this relation, energy is power times time. How quickly you're using energy times how long you do that for would be how much energy you've used. The power company, they bill you using the following units. Let's say you used a 1 kilowatt microwave for 1 hour. Well, that's called a kilowatt hour. A 1 kilowatt appliance drawing power or drawing energy for 1 hour uses 1 kilowatt. See, 1 times 1, kilowatt times hour. But that would be, here. A kilowatt is 1,000 joules per second. And an hour is 3,600 seconds. So you can check the number of zeros here. That comes out to be 3.6 megajoules. Okay, so this is the number I have memorized because it shows up often, but this costs you about 15 cents from the power company. It's equivalent to 3.66 megajoules. So 36.46, excuse me, times 1 kilowatt hour for every 3.6 megajoules. Well, 36 over 3.6, this is roughly 10 kilowatt hours. And that's an interesting number because I happen to know that that's roughly how much energy is used on a daily basis by a small household. So a household of 1 or 2 people with a couple appliances, especially during the winter when they're not using their air conditioner, they go through about 10 or 15 kilowatt hours per day. Wow, so this small room that we're talking about, this is a modest-sized room. If you could somehow extract the energy associated with the sub-microscopic kinetic energies of all the particles, if you could extract all of that energy, you could run your home for a whole day. How awesome would that be? Because you could just, every day, just, open up the doors and windows or the ventilation and let another room full of energy come in and run your house for another day. How come we're not doing that? We're prohibited from doing that by something, well, something that we call, as people, we call the second law of thermodynamics. And that shows up at the end of the chapter, and it's featured in the following chapter, chapter 21. Now, there's one other thing I should say pertaining to this problem. I'm suggesting that the total energy here would be number of moles times 5/2 RT, where I use the equipartition theorem to get this. And that would mean if I were to increase the temperature by some small amount dt, the total thermal energy would also increase by an amount dE. So let's take the differential of both sides. And 5/2 are dt. So this tells us how the increase in energy relates to an increase in temperature for this ideal diatomic gas. But then we can go back to the first law of thermodynamics, where the change in energy of any thermodynamic system, like a gas, would be the heat that enters plus the work done on the gas. And then we can ask how much heat is required to raise the temperature of 1 mole by 1 Kelvin at constant volume. So by definition, this is the constant volume heat capacity, molar heat capacity. So we say that the amount of heat required would be the number of moles times the molar heat capacity at constant volume times the change in temperature. So here, this is more general. It doesn't have to be 1 Kelvin. But this C sub V would be this quantity. C sub V is how much heat is required to raise 1 mole by 1 Kelvin at constant volume. That's this number right here. So if you want the amount of heat required to raise n moles by delta T kelvins at constant volume, you would use this formula. Now, constant volume means that there's no work being done. So I'll say equals 0 for constant volume. And that means that the heat required to do this is equivalent to the change in the thermal energy. Since you're not changing the volume, you're not doing any work or letting the gas do any work, whatever heat you put in shows up as an increase in thermal energy. So how about I now use the differential form. I'll take this equation, see I've eliminated work, and I'll write it instead as a tiny change in energy would be a tiny change or a tiny quantity of heat added. Well, a tiny quantity of heat dQ would involve an infinitesimal change in temperature. So dE would be equal to NC dt. Okay, so this equation follows from my series of logical statements about heat capacity. But if you compare that to the one we got up here from the equipartition theorem and the recognition that all the energy comes from the kinetic energy, I'll just rewrite that down here. We just compare the two. And evidently for a diatomic gas, there's the heat capacity. Diatomic gas, the heat capacity at constant volume, specifically constant volume, not C sub P, CV. That should be 5/2 R. Now, here's something that I find helpful. I just memorized that 1/2 R, well, that's 1/2 of 8.31 joules per mole Kelvin That's roughly 8, right? 8 divided by 2. This is very approximately 4. So I have that memorized. Half R is about 4. And that means 5 times half R would be about 20. I'm going to say very roughly 20 joules per mole per Kelvin. And now we can solve the mystery that showed up, I think it was in the previous chapter. Let me pull up the image from the book. You may recall from chapter 19 that they presented a table of molar heat capacities for various gases. You've got monatomic in a category and then diatomic. We're talking about diatomic gases right now, like nitrogen and oxygen. And you'll notice that under the column for CV, all of the heat capacities at constant volume are very close to the number 20. Now, that 20 is just a rough estimate. Remember, I approximated R over 2 as 4, but maybe you should do this on your calculator here while I'm going through it. I'm going to take R over 2, that's actually 8.31 divided by 2. So R over 2 is more like 4.15 or 4.16. And since I've got 5 degrees of freedom for the diatomic gas, I'll take that 4.16 and multiply it by 5, and I get 20.775, which I'll just round to 20.8. So in some sense, we've explained this 20.8. We've explained the coincidence here. Now, I can't account for the fact that these are all slightly different, but that's pretty darn encouraging that we've discovered something, some fundamental truth about, I don't know if I'd go so far as calling it a fundamental truth, but there's something accurate in our model of gases. And what is the model? It's this equipartition theorem. So 2 very different ideas here. I'm going to go back to the notes. These 2 equations came from different places. This one came from really 2 steps. We started with the definition of constant volume heat capacity. Where is that? Right? This is the definition of constant volume heat capacity. It's the amount of heat required to raise a quantity of gas by a given temperature at constant volume. But then I use the first law of thermodynamics to recognize that since there's no work being done, that quantity of heat is the same as the change in the energy. And then I just use the differential form of that equation to wind up here. So this comes from the first law of thermodynamics and the definition of molar heat capacity. This came from the equipartition theorem, the recognition that all the energy comes from these translational movements of the individual particles and their rotational movements, and the idea that the amount of energy in each mode, as your book puts it, would be 1/2 RT for each per mole, and we multiply by the number of degrees of freedom. 2 totally different ideas. We arrive at similar looking equations, so this allows us to theoretically predict. That's a theoretical prediction of the molar heat capacity. The table that we just looked at, those were experimental values. Those were measured in the laboratory. So how cool is that you can predict something that you can then confirm in a lab, but your predictions were made about tiny little objects that you can't even see. It's just your imagination. It's just a model that we've constructed. Well, somebody else constructed. Okay, so very cool. Is there anything else we can add here about that? Yeah, I'll just remind you, it's worth knowing that half R, 8.31 divided by 2 is 4.15. Oh, that was the other thing I meant to point out. Remember from the previous chapter, another result was that for an ideal gas, we found that this came from the first law of thermodynamics, I believe. The heat capacity at constant pressure is always the heat capacity at constant volume plus R. All right, so for diatomic, CP would be, well, we've just determined that CV would be 5/2 R plus R. Well, this R is the same as 2/2, 2 over 2 times R, so 5 plus 2 is 7/2 R. 7/2 R. And then gamma, the ratio of heat capacities, CP to CV, that's easy now. We've got 7/2 R over 5/2 R. And that comes out to be 7/5. Put that into the calculator. 7 divided by 5, 1.4, which was in fact the value that we used for diatomic ratio of heat capacities in the previous chapter. So we've predicted that as well. I sort of have this memorized, that for diatomic, gamma is 7/5. Let's do monatomic while we're at it here. We know that CV is only 3/2 R. Right? This is how many joules there are per mole per degree Kelvin. CP would be CV plus R. 3/2 R plus another R is 5/2 R. And that means for a monatomic gas, ideal gas, the ratio of the heat capacities, gamma, maybe I could put gamma dia and gamma monatomic, would be 5/2 over 3/2, or in other words, 5/3. So I sort of have that memorized because there's an easy pattern there. See, it's just consecutive odd numbers. And as you go up to more degrees of freedom, you're dealing with higher integers. 7/5 for diatomic, 5/3 for monatomic. Those are the theoretical values.